Morning, everyone. It is my pleasure to introduce Seth Jacobson for the seminar today. Seth went to Cornell for his undergrad, like me. Very exciting. I love seeing Cornell people's CVs. He graduated later, of course, in 2008. During that time that he was an undergraduate, he was an intern at the Geophysical lab, like me too, which is super exciting. He worked with Burkhard Militzer, and then he went on to CU Boulder and got his master's and PhD in astrophysical and planetary sciences. He's now a professor, an assistant professor at MSU in Michigan, where it's this cold all the time.
That's right.
And he's an expert in the dynamics and evolution of solar systems. And he's been super kind and agreed to lead our Carnegie Planetary Reading Group tomorrow. So come for that as well. So thank you for coming, Seth.
Thank you very much for having me. I'm excited to return to Carnegie. I think I've only been back here once since I did my internship in 2006, but I have very fond memories of that summer, and I learned a lot. I learned a little bit about density functional theory, but I learned a lot about how to do science while I was here, and what being at a research institute is really like. Today I wanted to talk about a project that started during my postdoc with Dave Ruby and Alessandro Morbidelli, which was a combination of bringing together astrophysics and geology into a single cohesive modeling effort to understand the formation of the terrestrial planets. And so a part of this talk will be going through those results that have come out in the last 5 years, and then it'll end with a lot of new material on what might have, what's really in the title of this talk, which is what might have gone wrong at Venus or right at, let's, I guess, not take a judgmental stance, but what made Venus and Earth, or what potentially could have been responsible for the differences that we see today. And then, another way of phrasing this is it surprising that Earth and Venus are so different? And I think it really is surprising. From an exoplanet perspective, these two planets would read as nearly identical. And yet we know as planetary scientists that there are at least 5 really distinct differences from the presence of a moon, the presence of a planetary magnetic field, the mass and composition of the atmosphere, the mantle convective regime or the mantle heat transport regime, and the spin state. And there you can list some other minor differences, but I think that those 5 really dominate the differences between these two planets and ultimately mean that one is verdant and full of life, and the other one is a place where spacecraft built like submarines last minutes, right? So these two planets are incredibly different, and so I think in the context of both exoplanet exploration and understanding our own history, we really have to get to the bottom of this question. All right, so the plan for this talk is to break it up in 3 parts. Briefly review terrestrial planet formation so that everyone is on the same page when I talk about things like planetesimals and embryos, and then introduce this joint astronomical-geological model that was really started at the Bayerisches Geoinstitute by Dave Ruby, and then I handed off to me, and I've taken it in a number of different directions. And then we're going to use that to understand some results in mantle composition, in the construction of core structure on both Earth and Venus, and then talk at the end about water in the interior and what a different accretion history means for the composition or for where water ends up inside of a planet. And then lastly, I'll talk a little bit about some work I've been doing with a student on what happens to moons that are formed during or inside the protoplanetary disk. All right, so let's start with this review of terrestrial planet formation. So at the very beginning, the geologists often make this mistake of thinking that time zero on the Earth is a fully formed Earth that's sort of a molten ball of silicate liquid that's just gone through core formation. But that's not really time zero for the Earth. Time zero for the Earth is really when it's a mote of dust floating in the solar nebula and it starts to grow and accrete. And so you start in the solar nebula as these sort of monomer-like particles that grow by a process of sort of pairwise accretion up to some growth limit. And those limits we think are a series of barriers that people can have shown to exist in laboratory experiments, low or no gravity in drop towers, so they achieve very low gravity, and then they throw dust particles at each other. And what they find is that intermolecular forces do a good job of binding these monomers up to a certain size. And then above that size, no matter how gently or hard you throw these dust particles at each other, they don't stick anymore. They either bounce or they can even fragment and go to smaller sizes. And so that you end up at this bouncing or fragmentation regime, which for the rest of this talk I'll refer to as the Pebble size regime. This is a name that I think originated with Anders Johansson. But these pebbles, that's just to give you some sense of the scale of these objects. They're between millimeters and decimeters in size. But they're going to not look anything like river stones. They're going to look very different ultimately. And the cool thing, though, is that this is all theory and laboratory experiments. But when we take large radio telescopes and look at disks, this is a very famous image of HL Tau taken by ALMA, we see pebbles. And we see disks filled with these pebbles, these objects that come from this growth process and end up with these final sizes. So a big regime of study is then how do these pebbles form planetesimals? And so because we run into this barrier from pairwise growth, we know it's unlikely to be from binary collisions. And so a number of different ideas have been put forward in the last few decades to effectively accumulate, using solid gas interactions, large quantities of pebbles in one location. And if you can accumulate enough of them in one volume, that those pebbles in that volume will go gravitationally unstable. And so they'll start to fall inward due to their own self-gravity and collapse into a single object. And I don't have time to go into a lot of details of this process, but what's really cool is that simulations of this process seem to match the preserved planetesimal population in our solar system, that is the cold classical region of the Kuiper Belt, really well. And so it predicts a certain, a very high fraction of binaries, and so this process also produces, this process produces a lot of binaries, and we see a lot of binaries in the cold classicals. All right, so these solid gas interactions, there's a number of different ways that pebbles can be accumulated into these gravitationally unstable clumps. And so this is how we think planetesimals form. In other words, they form big, and you might have heard that expression before, planetesimals are born big. And there's also some evidence from the asteroid belt that that's the case. So there are two now theories for what happens to this planetesimal population. One theory was really started at Carnegie. It was really the child of George Wetherill. And this is this idea that from a sea of planetesimals emerge the final planets through, again, binary or pairwise collisions. And so these are some frames from a classic paper on runaway growth by Kakuba and Ida, showing that from a sea of planetesimals, in very short order, through this runaway growth process, you end up with a chain of oligarchs, or with some leftover planetesimals in the simulation. And so what ultimately happens is from the sea of planetesimals, the largest objects, due to this gravitational focusing factor, which is really George Wetherill's contribution, you establish a bimodal mass distribution. And the largest guys grow fastest, and you end up with this bimodal mass distribution. Now, another process has been introduced that competes with this planetesimal accretion regime, and we call this Pebble accretion. So this is the direct accretion of lots of those small objects that have grown through pairwise accretion up to the fragmentation or bouncing barrier, and then are directly accreted by the planetesimal population to lead to rapid growth. So I'm going to start this simulation to show you what happens for these pebbles. So this is a planetesimal passing within the deflection range of this planet. Let me pause it. Okay, so let's watch this planetesimal fly by. It's only experiencing the forces of gravity. And so because of that, it enters the potential of the central embryo. Sorry, I'm struggling to play this. It enters the potential, but because it doesn't collide, it then exits the potential. So it speeds up, but then that exchanges that energy for potential energy, and it moves back out of the potential. But for a pebble, something very different occurs because the pebble interacts strongly with the gas in the solar nebula. As it speeds up and falls into the potential of the central embryo, it feels and experiences aerodynamic drag. And the aerodynamic drag leads to energy loss. And so then it doesn't have enough kinetic energy to go up the other side of the gravitational potential. And it gets trapped in the well of the embryo. And so this can lead to the trapping of huge quantities of these pebbles, depending on the pebble surface density in the disk, and lead to the rapid growth of embryos. And so just by changing the properties of the pebbles in the disk, you can go from a regime where you grow Mars-sized embryos in a few million years to growing something that looks more like the core of Jupiter, about a 10 Earth mass embryo. And here all we're changing is the Stokes number of the pebbles. And we're actually only changing it by a factor of about 15. And that leads to vastly different growth. And so crossing the ice line might change the properties of the pebble, and that might be responsible for why in the outer solar system we grew large cores, and in the inner solar system we were left with these small embryos. And then again, though, we end up with a population, a bimodal population of large embryos, and maybe some leftover planetesimals in the inner solar system. And so from this population, this bimodal population of embryos and planetesimals, people have done simulations. People like John Chambers, and I actually haven't seen him yet, but a Carnegie scientist. And what's really amazing is just from these simple starting conditions, you can grow the terrestrial planets quite accurately and quite well. And so this was a big triumph of this theory. There were a number of immediate successes. Generally, you create the correct number of planets. You get the right a match for the mass of Earth and Venus. Relatively good orbits. You get giant impacts, which we know are necessary to form the moon. And we also get radial mixing. So we can explain why the Earth, which might have formed in a very dry region of the disk, received water from the outer parts of the inner disk. So, but one of the challenges was that the planets at the location of Mars were too large, and this was a problem that persisted for about a decade. And so in 2009, Hansen proposed that we could start from just a truncated disk. He was actually studying disks around white dwarfs, and he realized that the problems he was studying were analogous to the terrestrial planet system. And the nice thing about starting with a very narrow annulus is that you could reproduce the mass orbit distribution of the inner solar system. And but this was unmotivated. Hansen was studying white dwarfs. He didn't have an explanation for why the terrestrial planet, the disk around the sun, should be truncated in this manner. And so Kevin Walsh and colleagues came around and using results that really were inspired by the exoplanet science, came up with this idea that perhaps Jupiter and Saturn migrated into the inner solar system and then turned around and migrated back out of the inner solar system. And I don't really have time to go into why the hydrodynamics work out in that way, that they would switch direction of migration, but it's actually a really robust result that lots of groups had seen prior to the suggestion that this actually occurred in the inner solar system of our solar system. And this is nice because it generates this mass orbit distribution that looks just like the terrestrial planets. But even more recently, another Carnegie colleague of yours, Matt Clement, proposed an alternative to the Grand Tack, and this is an early giant planet instability. So we know that there probably was a strong hypothesis that the giant planets underwent a dynamic orbital instability at some point in their histories, because the giant planets actually have significant eccentricities and inclinations to their orbits. And this is a very unexpected feature for the growth of giant planets, unless they had strong interactions with one another. The timing of that instability, though, has been greatly debated. It originally was attached to a late heavy bombardment of the Earth, or of the Moon, rather. And the suggestion was then it would take place hundreds of millions of years into solar system history. If such a bombardment occurred, it's after the end of terrestrial planet formation. And it was shown by John and Matt that this is actually really bad for, or were you on that paper, or was it you and Nate? It was before your time. It was Nate and John, I think, that's right. It was Nate Cabe and John Chambers that showed that it actually would destabilize the terrestrial planets. And so having such a violent instability was actually really bad for the growth of the terrestrial planets. And so what Clement showed is that if you had this terrestrial planet instability very early, you were able to shape the disk, the terrestrial disk, prior to the final accretion and final assembly of the planets. And so you were left with just a few planets that followed this mass orbit distribution. I should point out, make these plots more clear. Each of these black dots are planets that came out of a large suite of simulations. So this isn't just one simulation, the planets that came out of one simulation, but came out of a lot of simulations. And they're all plotted on top of each other to give some sense of what just the general pattern of where planets grow as a function of their orbit. And so you can see that an early instability does a good job of matching the orbits of the terrestrial planets. But I think one of the key takeaways is that we now have multiple ways of matching the astrophysical data of the terrestrial planets. We now have multiple histories that we could suggest for the solar system that can match their masses and their orbits. And we need to bring in alternative data to sort out which of these models are correct. And that alternative data I'm going to propose is the geologic data of the Earth and the other planets, and it can be really used to great effect. So just to summarize how planets grow, or terrestrial planets grow, we think that it occurs in 3 stages. The first are these condensates and prestellar grains accumulate up to the bouncing barrier in size, so up to that Pebble threshold. And then these pebbles are collected by solid-gas interactions and go through gravitational instabilities to form larger planetesimals, perhaps objects hundreds to 1,000 or so kilometers in size. And then these planetesimals grow to embryo sizes or planetary sizes via mutual collisions, i.e. the Wetherill model of planet formation, or through Pebble accretion, this much more modern idea that the planets grow directly from the Pebble population. Okay, so now that we've gone through this review of how we think the general pattern of terrestrial planet formation occurred, we can start digging into this joint astronomic-geologic model, and I'll demonstrate to you how we're incorporating a lot of geologic data into our astrophysical models of planet formation, and then how we can rule out or in different models of planet formation. Okay, so the idea, generally speaking, is to take our astrophysical n-body simulations and then incorporate high-pressure laboratory experiments of partitioning between metal and silicate. So we can model the core formation process of the planetary differentiation process in detail that's ongoing inside the planet during planet formation. And so in order to do this, we need to have some guesses as to what the building blocks of the terrestrial planets are. And what we're going to use are the compositions provided to us by the different chondritic parent body reservoirs. So we have the carbonaceous chondrites, the ordinary chondrites, and the enstatite chondrites. And we have this trend of volatility through the solar system. And so these are just some pretty pictures of different chondrites. We know that using chondrites is a good, chondritic compositions is a good starting basis for such a model, because the chondrites actually match the composition of the sun very closely. So this is a classic plot that sort of showed this for the first time, showing each of the different elements, abundance in carbonaceous chondrites versus the sun relative to silicon. And you can see that almost all of them fall very closely to the 1-to-1 line. Similarly, we can see in the Earth's mantle, these are the red points in this plot. which show the abundance of various volatile elements normalized to silicon and this C1 or Ci carbonaceous chondrite as a function of condensation temperature. So elements with very low condensation temperatures are taken to, we can infer that they're more volatile, and then if the condensation temperature is higher, we can infer that they're more refractory. And what we can see is that this volatility trend in the Earth, which are these red points, is similar to the volatility trend we see in meteorites. And so this idea that the volatility of the trend in the Earth was likely inherited from from the disk, just as the chondrites inherited a very similar volatility trend. And the way we work this into our model is we assert an oxidation gradient in our disk, as well as various volatility gradients in species like sulfur and carbon. Here I'm showing the oxidation gradient. And what we can see is a very highly reduced part of the inner disk. And then we have a partially oxidized part of the inner disk, and then an outer disk that's almost fully oxidized. And when we incorporate water ice interacting with with carbonaceous chondrite-like material. So we're assuming something that looked carbonaceous chondrite-like plus about 28% water, and letting that all interact in our planetesimals to give us a final composition and oxidation state. So I mean, broadly, we can think of this as sort of the N-type chondrite region, the ordinary chondrite region, and a carbonaceous chondrite region. So that's the starting place for this model. And then, so if we have our initial conditions, we need to then be able to compare what do our after we run the model, what do our outcomes, what are we going to compare those model outcomes to? And we take rocks from the Earth's mantle as our primary point of comparison. So we use mantle periddotites, which are these are two examples, I think both from the San Carlos olivine. And they, so these mantle periddotites, what's beautiful about them is they can be collected all over the world, and they have very similar compositions, suggesting that the upper mantle of the Earth, at least, is very homogeneous in its composition. All right. So that's what what that looks like in sort of a quantitative form is this figure. So here we have the abundance of each of these elements in the Earth normalized to the carbonaceous chondrite. So if an element is abundant in the Earth's mantle at the same relative abundance to titanium as in the Earth is in the carbonaceous, the Ci chondrites, or in effect the sun, then it's going to plot along this dashed horizontal line. So things like calcium and aluminum plot up there. And then we see that same volatility trend that I showed you a couple slides ago. But we also see a number of elements which are quite refractory are missing from the Earth's mantle. And so this is the siderophility trend, and shows how these elements have been drawn into the core of the Earth, and so they're less abundant in today's mantle. And so this is an observation that was made quite a long time ago, and people have done a lot of laboratory work to explain this depletion of these different siderophile elements. And this is an example of work done in the 90s. These are high-pressure laboratory experiments. This is the various the data points, and then the fit to the data. And so this is for an example where they've done a number of experiments at a given oxygen fugacity for nickel and for cobalt, and they're changing the pressure of the experiment, and then the experiment is giving them a partitioning coefficient. So how much of a given element goes into the metal versus into the silicate liquid. And the conclusions of this paper were that we looked at the previous plot for nickel and cobalt, they plot very close to one another right here, which implies a certain partitioning coefficient in a very simple model. And then they could read off the pressure and temperatures of equilibration and infer something about how the planet formed. But of course, this makes some really enormous assumptions in doing interpreting these experiments. It asserts that the entire mantle, for instance, equilibrated with the entire core at a single pressure and temperature, and a temperature and pressure which are significantly lower than the core mantle boundary pressure and temperature, for instance. And so this is very suggestive that equilibration occurred much higher up in the mantle than at the core mantle boundary pressure, but it also then suggests that we have a lot more modeling work to do to interpret what's going, the bulk chemistry of the Earth's mantle. And so that's what Dave Ruby and I set out to do. So we took our n-body models, which give us a history of planet formation, and we took the fact that our n-body models also tell us where all the planetesimals and embryos in the simulation come from. So then we can relate them to that oxidation gradient, to that volatility gradient, and so we have our initial conditions, and then we know how they're processed, how they collide with one another, and how they chemically interact. And we use a very simple model for that. That's a multi-stage core formation model. And it's multi-stage because we're running this model every time there's a collision between two planetesimals or a planetesimal and an embryo in the simulation, or an embryo and an embryo in the simulation. And so during each accretion event, we strip the mantle from the projectile. We allow the projectile core to equilibrate with a fraction of the target mantle. And that fraction is dictated by fluid experiments done in a laboratory by Renaud Degouin. And then we allow that equilibration, that chemical equilibration, occurs according to those partition coefficients which come out of these high pressure laboratory experiments. And then finally, the equilibrated metal accretes onto the core, while the mantle vigorously convects and mixes the remaining silicate liquid back to the mantle. All right, so we're running this process after every accretion event. What's interesting is because the Earth is growing during this process, the equilibration pressures and temperatures are naturally increasing inside the planet. So for our simple models, we're asserting that the equilibration occurs at some constant fraction of the core mantle boundary pressure and temperature. So that's what I'll be presenting to you first. And it turns out that our best fit solutions have that occurring at about 70% of the core mantle boundary pressure. And so that's what's shown here, is that equilibration pressure is a function of time. The temperature is fit to be the midpoint between the solidus and the liquidus of peridotite at this temperature, or at this pressure rather. So it just comes from the equation of state. What we can see as the planet grows, the equilibration pressure and temperatures naturally rise with the planet. And that makes a certain amount of intuitive sense. You're not going to have high pressure events on a small planet. And when you have a larger planet, you're likely going to have equilibrate at the base of a deeper magma ocean. Yeah.
So if you have a violent impact like a planetesimal hitting the Earth, or going to be superheated, how long would it take to equilibrate with the mantle?
That's a good question. We found that overstepping the temperature, we experimented with that, where we had the temperature overstep by some amount. We found that moderate overstepping of the temperature didn't affect the results a lot. You could get up a couple hundred Kelvin, didn't change the results very much. However, if you overstep by thousands of Kelvin, you can get radically different results. And so some people have suggested that, for instance, magnesium entered the core early on, or during the era of planet formation, and then was exsolved, and that drove the early dynamo. And one of the ways to get that is to have exactly what you're suggesting. During the impact, you superheat the region of equilibration, and that definitely helps force a lot of magnesium into the iron liquid. So absolutely, that's something to think about. Okay, so for these, so here's our results in terms of nickel and cobalt to compare to these earlier results. So each of these plots, we can read the dashed line is the abundance of nickel and cobalt in the Earth today. And what we can see is that nickel and cobalt, they accumulate in Earth's mantle, and that's because both of these elements become less and less siderophile as a function of their pressure. And so as the pressures of equilibration increase, they become less and less siderophile, they accumulate in the mantle, and that's what we can see right here. Other elements don't behave the same way. Some elements become more siderophile with pressure and temperature, or whose their siderophility don't change. And so we can look at all these different elements, and so this is a plot of the from Ruby's our paper in 2015, Ruby et al. 2015, and we're showing iron, silicon, nickel, cobalt, niobium, tantalum, vanadium, and chromium, and water as well. And on the far right side of each plot is a little black bar, which shows the Palma and O'Neill estimate for the abundance of that element in the Earth's mantle today. And what we're showing is 3 different numerical astrophysical models that show how these elements accumulate in Earth's mantle as a function of time. And so we can see that some elements behave like nickel and cobalt. They accumulate in Earth's mantle, so early on there's less of them present. And then other elements increase in siderophility with pressure, and so they're drawn down into Earth's core through subsequent giant impacts. And so this really successfully reproduces the composition of the Earth's mantle, and we can all we're really adjusting is where in the disk is that enstatite zone, ordinary chondrite zone, and carbonaceous zone. And then this constant factor of core mantle boundary pressure. All right. So another question we can ask is what happens to the equilibrated metal in these conditions? And so when the equilibrated metal disappears down to the Earth's core, 3 things could potentially happen. If it's less dense, it could form a layer on top of the core. If it's about the same density, it'll just get mixed in with the core. And if it's of a significant higher density, it'll actually continue through the core and probably form a layer deeper within. And so you can derive a condition from fluid mechanics for whether these different layers will be unstable or stable through a Rayleigh number analysis. And so that's what we did here. Now, just to back up a step, generally speaking, as we increase the pressure and temperatures of core formation, that increases the siderophility of light elements in those equilibrated metals. So the abundance of silicon and oxygen increases with time or as the pressures and temperatures increase, and that drives down the iron and nickel content correspondingly. And so overall, there's less iron and nickel and more silicon and oxygen. That means that the layers, the layers follow this upper path, and so we're generally forming less dense layers on top of our core, and we form a stratified core. And so we can put this all together, and here I'm showing as a function of core radius what the total light element abundance would be once we've performed our Rayleigh number analysis after each accretion event. And what we find is that we find a very large light element stratification at the top of the core, almost 1,000 kilometers in extent. And what this and here's the same plot, but just showing density as a function of core radius to show just how significant this effect is on core structure. And what this would effectively do is create a bunch of conductive bands at each of these steps between the layers that would inhibit convective motion inside the core. And so you'd end up with something that looked a lot like an onion. And within each of those layers, it's possible to have convective motion, but not across those layers. And this would effectively shut down convection in the core, with the exception of maybe in the topmost layer. And so this would probably lead to a core that had very little dynamo action. Now, of course, you're thinking, well, that's nothing like what the Earth looks like. The Earth has a dynamo. The Earth has likely has a convecting core. So what did we leave out? And what we realized we had left out was the mechanical mixing that comes with large impacts. So when you have violent impacts, and here are 3 simulations by Nikki Makijima that show very violent impacts. This is the sort of standard canonical moon-forming impact This is a kind of impact that looks a lot like what Sarah Stewart's been talking about that forms a synestia. And this is what Robin Canutt proposed, where you had two equal-sized Earths striking each other. And in each case, you can see that the gray core region is very distended and distorted by the violence of the impact. And what that means is that there's mechanical energy or kinetic energies going in and mechanically mixing the core and could destroy those stratified layers. So what we did is I worked closely with Miki Nakajima, and we came up with a scaling relationship from these, from SPH simulations very similar to these. And so that's what's being shown in this somewhat complicated figure. The x-axis is the mass of the projectile. And then there are two plots, one showing impacts that take place at sort of the escape velocity of the Earth. So this corresponds to sort of the canonical impact regime, and then down here 3 times the escape velocity. So this would be a very violent impact that's much more similar to what Sarah Stewart's proposing. And then we have this mixing efficiency along the y-axis, and that's suggesting how much of the kinetic energy of the impact goes into mixing of the core. And we came up with a way of measuring this by comparing the potential energy of the core pre and post impact. And what we think from our simulations is that most impacts, the mixing efficiency is about 4%, give or take about 4%. So it's somewhere between 0 and 10%, I would say, is the mixing efficiency of a given impact, depending on things like the angle of the impact angle and other aspects of the geometry, such as rotation. And then what's shown in these contours is how much of the core stratification is removed then. And so whether it could be 1% is removed, it's more or less the core stratification remains. And then over here is the 100% contour. Everything to the right in this gray region, you end up with a fully mixed core. So you've removed all the stratification. You've done the work necessary to bring the dense parts up and the less dense parts down. And so what we see is that for moon-forming impacts, where even in the canonical regime, where you have a Mars-sized impactor striking at roughly the escape velocity, you're very close to this point right here, where you get 100% mixing, and you're completely have homogenized the interior. With this dashed line here shows what happens when Ceres strikes the Earth. And so we can see that even a very large dwarf planet, something nearly 1,000 kilometers in size, no matter how hard it strikes the Earth or what geometry it strikes the Earth, it's not going to do 100% mixing. The core stratification is robust to that kind of impact. So a planet that grew only from small impactors, its core is going to remain stratified. Whereas if you had a large, giant, violent impact at the end of accretion, it's going to completely mix your core. And so this is another way of seeing this. This is by taking the same planet with the same accretion history, so a very good Earth-like planet. It matches the Earth in every astrophysical parameter, and then changing that accretion impact efficiency from very low, so only a tiny amount of the energy goes into mechanical mixing, to about 5%. We can see that we can completely erase the core stratification. Okay, so what we're seeing is that a giant impact on the Earth is probably necessary to create the conditions for a geodynamo, to create a single convective unit in the center of our planet. And we can generate sort of a corollary hypothesis from this work, and that is that if Venus suffered no impact or a series of less violent impacts, then conductive banding inside the Venusian core could inhibit a dynamo. And I can go even a little bit further than this and suggest, when we look at our two smaller terrestrial planets, Mars and Mercury, one planet, Mercury, because of its large core size, there's some suggestion that it suffered a violent impact, and it has an active dynamo. Whereas Mars, there's the largest impactor on the surface of Mars, or that we can infer is potentially the Borealis Basin, which would be small enough that it wouldn't likely stir the core significantly enough to remove conductive banding. And so there's this potential to extend this to the smaller terrestrial planets as well.
So
That's a great question. So that's exactly what this slide addresses. So what we did is we took all of our simulations that make a good Earth and a good Venus, which is most of them, and we plotted for each planet. We calculated what the core mixing fraction would be. And this plot's a bit silly because it goes beyond 1. And if your core is fully mixed, it's fully mixed. Doesn't matter if it's twice fully mixed. But these planets receive significant mechanical energy into the core, whereas these planets over here, for the Earth-like planets, didn't receive enough. And so their cores remained stratified. And this was for a fixed 4% mixing efficiency. Now we did the same thing for the Venus-like planets on the y-axis. And so here, the planets below 1 are completely are stratified, and those above 1 have lost their stratification. And so the gray region marks out a territory, to answer your question, where in our simulations at least, you have a Earth-like planet that's has lost its stratification, and the Venus-like planet hasn't. And to get to the why of it all, it's because the Venus planet generally accreted from a lot of small embryos, where the Earth-like planet got hit once first off late in accretion, after all the planetesimals for the most part have been accreted, and by something a little bit larger. And we do have evidence from the highly siderophile elements that there wasn't much planetesimal accretion on the Earth after the moon-forming impact. A prediction from this hypothesis would be that Venus would have a large highly siderophile element abundance in its mantle rocks, because its core formation ceased much earlier than its planetesimal bombardment. All right, so that's exactly what I said here. Late on Earth, early on Venus. That explains what's going on. So here I'm showing the time of the Earth-like final giant impact on the Earth, and we see they all fall in this range. And on Venus, you can have impacts on the Earth that take almost 100 million years before the Earth is hit. That's the star. That's actually the simulation that I showed throughout the talk. And on Venus, the last final impact on Venus was just a few tens of millions of years. And the planetesimal bombardment on both planets is not as stochastic because there's a larger number in it. And so it's the same on both planets. And so both see the same 100 million year roughly long planetesimal bombardment. But the stochastic or large impacts, which there are just a few of, can occur with a very different frequency. All right, so that's what I'm trying to say here. There's a big difference between giant impacts and planetesimals. So all the planets, Venuses and Earths, are all plotted on this figure, which shows the time of the last giant impact, and then how much mass is accreted after that giant impact. And so they all follow in a single line because it's a single decaying in the abundance of planetesimals with time. And the cool thing is, because we have measurements of the highly siderophile elements abundances on the Earth, we can infer a late accreted mass, or how much planetesimal material was accreted by the Earth after the core formation on the Earth, and that corresponds to this dashed line. And so we're able to read off the time of the moon-forming impact on the Earth, or the time of the end of core formation on the Earth. And so what I'm suggesting here is that for Venus would be one of these other dots in further up this correlation, and you would see something like perhaps a tenth of Venus's mass coming after the end of core formation, after its last giant impact. Okay, so I am running short on time, and so we'll try and go a little bit quicker through my water story in 4 minutes or so. We can assign water a water volatility trend in the same way that we did for oxidation. So we can associate the inner part of the solar system with andesite chondrites, ordinary chondrites, and carbonaceous chondrites, and then look at their water abundances. And here is a nice plot that also shows where the Earth falls between andesite and ordinary chondrites. Yes. Okay, so when we, in our numerical simulations, as we watch the terrestrial planets accumulate water, we note that the water doesn't come just at the end of planetary accretion. That's an idea that's been proposed at times, No, what we find is that water water from the carbonaceous chondrites starts to be added into the inner solar system progressively, but starting relatively early in Earth's accretion. So the radial mixing is quite vigorous in almost all of our numerical simulations. Oops. And that's consistent with other nucleosynthetic isotopic anomalies. I don't really have time to go into this plot in detail, but what it suggests is that the material that the Earth is accreting doesn't change over time. It stays fixed throughout Earth's accretion, and that's because molybdenum and ruthenium are partitioned differently in the Earth during planetary differentiation. Okay, so here's our time of last giant impact for our terrestrial planets, Earth and Venus again, and then this is the percent of water accreted into the Earth's mantle before the last giant impact. And we find this nice correlation. Of course, it makes sense. If your giant impact is very early, then you're going to accrete all the water after the giant impact. If it's very late, you're going to accrete the water before. It's a very sensible relationship between how much water is accreted prior to and after the last giant impact. And we can look at this as like a stratigraphic record. And this is, I admit, a bit silly of a way to look at it because these layers aren't going to stay like a nice sedimentary sequence. But we can think of it momentarily or as sort of a figurative way of looking at the Earth. So here's the Earth's mantle as a function of radius. And if we accrete N-type chondrites or material local to the Earth's formation region, they have about 10 ppm of water. If they're ordinary chondrites, maybe 1,000. If they're some combination of the two, they're in between. And then we have the carbonaceous chondrites where we've asserted that there's at least 20 weight% water along with the carbonaceous chondrite material, and they're over here. And so you can see as these objects come in and hit the Earth, you could think of them as a stacked sequence of different objects, and we get some water arriving from the carbonaceous chondrite region relatively early, but then more and more as we increase. And so we can look at two different Earth-like planets, one with a late last giant impact and one with an early last giant impact. And I'm showing this stratigraphy again just to show you that the timing of the giant impact doesn't actually affect any of the other impacts. So these two figures look very similar. You have you start with a lot of local material, and then you get to a point where it's all mixed, and you're getting stuff from the outer part of the disk and the inner part of the disk at some relative rate. Okay, and so this is preliminary work, and so we're making some really radically simple assumptions, like such that magma ocean mixing is 100% efficient. But if the rock crystallizes, we're in a solid state convective regime that is on such long timescales that we're going to ignore it for now. And so there's no convection in the crystallized material. The impacts generate magma oceans with a depth that we can estimate from Mickey's simulations, and that we're not really taking into account the mineralogy and what that means for storage. But I've since sort of convinced myself that it doesn't matter anyways. So it's actually a relatively good assumption. So here's what happens to our two planets when we start processing what's happening in the mantle in a relatively more sophisticated way. We have our early last giant planet and we have our late last giant planet. And the big thing to take away is that the difference between the upper mantle in a planet with an early last giant impact is very different from the deep mantle. And that's because there are no late giant impacts to mix upper mantle material with deep mantle material. And so you have to rely upon solid state convection to do that work for you. Whereas if the last giant impact is late, then that giant impact does that work for you. And so you start with something that's much more homogeneous across the whole mantle. And maybe there's just that 0.5% of late accretion that delivers some water to the upper mantle. But it's a much smaller difference than in the case for an early last giant impact. We also find a feature that's relatively robust, which is that just above the core mantle boundary, we have a lot of material that was accreted very early. And because it's sort of protected by the mantle above, it rarely melts during accretion. And so because it stays crystalline, and this is very sensitive to the impact models that you put into the simulations, but potentially because it stays crystalline, it preserves a very different composition than the rest of the mantle. And that obviously has some interesting implications for things like low shear velocity zones and so forth. And where I'll end is just by saying, like, water, we know that water has big impact on how rock behaves rheologically. It can significantly change the melting temperature, and then just the presence of a little bit of water, 100 ppm of water, can be the same as melting 1% of a rock in terms of its viscosity and so forth. So I had another 5 slides, but I'm going to pause. I'm just going to go to the end of my talk, and thank you for your attention, and tell you that the accretion history matters. And so to understand the early Earth and the history of the solar system, one needs to incorporate both these astrophysical models, but also the geological models as well. And thank you for your attention. Yeah. So the answer to the first question is, when we calculated the diffusion timescales over the history, if a given boundary over the history of the solar system, it would you would get diffusion of about 100 kilometers. So, yeah. So that came out like Esther Posner did some experiments on diffusion of light elements in liquid iron, and so that's where that's coming from. So you get a smearing over the history of the solar system of a conductive boundary of about 100 kilometers from diffusion. The turbulence is, so we did effectively some dimensionless number calculations to see what would what the effect of what is the word I'm looking for, where waves from the convective region pass through the boundary, because those can also start turbulence at the boundary and potentially mix the layers. And so I'm forgetting the word for this style of mixing, but you're actually robust to that as well. It only takes a very small change in density to be robust against that. And so that's the short of it. But I think that there's a lot of space to work here in terms of, this is all done with sort of a dimensionless number approach, and I think that numerical simulations and higher fidelity calculations could definitely be done to test this hypothesis further.
Have you considered the consequences of late impacts on the temperature? I'm thinking that late giant impact, you're going to be delivering the core of that impact or the gravitational potential energy of a big planet. Have this big insulating layer. Thought being that another cause of the difference between Venus and Mars might be that the core of the Earth is unusually hot compared to the core of Venus. It also would drive things like pluming.
Yeah, I think you're right. I think that could be part of the same story. Absolutely. And and just in general, I think the hypothesis, the biggest way to say the hypothesis is that the Earth had a very violent end to accretion, and the violence of that end of accretion may be why explain a lot of the differences between Earth and Venus. And part of that is that you're going to reach much higher temperatures. And so I put it in terms of mixing water throughout the mantle, but you could also think of it in terms of just equilibrating the whole mantle with itself, and initially at a very high temperature. Yeah, so inside each of those shell-like layers, you could that's convective. That could, and so as long as there's something to be transported out, as long as there's heat to be transported out, you would have convection. So in those deeper layers, you probably would start off with some convection in those layers because you might have a thermal gradient that is super adiabatic. But then it's going to relax to an adiabat, which is set by those conductive boundaries. And once it relaxes to the adiabat, it's not going to be able to drive convection because the conductive layer above will force a certain heat flow effectively. That's what I had to skip, and the short of it is, I had a student work with me, and our takeaway message is that it probably wouldn't if it's a late giant impact, it probably should have a moon, and we don't see a moon. Whereas if it had an earlier giant impact, there's a strong possibility that planetary flybys inside the protoplanetary disk will lead to stripping of that moon. And the stripping of that moon would mean that it wouldn't have the moon today. So it's a really nice, the short argument of the last couple slides is that Raluca Rufu, when she was in Israel, she did a lot of studies with Oded Aronsid, and they showed that every giant impact makes a moon. It's just the size of the moon that changes after the giant impact, because every giant impact makes a little disk, and from that little disk, you create a little moon. And so what happens to all these moons, that's what my student tried to answer, and it seems to be that the protoplanetary disk is a very violent place, not from just the perspective of collisions, but also close encounters between bodies, and those close encounters can lead to stripping of moons. And so I think with Venus, you probably had big impacts that created moons, but they were stripped. And what makes Earth and Mars different from Venus and Mercury is that there was a big impact near the end that could make a moon. In Mars' case, it was a little tiny impact, the Borealis Basin impact, but that was enough to make the tiny little moons of Phobos and Deimos. Whereas we got slammed by a huge impactor, or an impactor going at incredible speeds, and that created this giant moon. Yeah, that's okay. The first part of the answer to your question is that the reason why in all of our simulations, the first couple 1,000 to 2,000 kilometers of these Earth-like planets are always relatively homogeneous. I guess the better way to show it is here, where I think it's homogeneous up until this point here at 1,600 kilometers. It's exactly what you say. When the Earth is tiny, it's easy to mix the core, and so the core becomes homogeneous relatively quickly. And so that's the problem with applying this. I mentioned that this could be applied to Mercury and Mars. That's the problem in a traditional sort of Wetherill style growth. You can't apply this model to Mars and Mercury. It would suggest that both of them should be well-mixed cores. But in a Pebble accretion scenario, where Mars and Mercury grew exclusively from pebbles, so no impact energy at all, more or less, was delivered to the surface of the planet, then you could potentially get both planets to grow with strongly stratified cores. And my initial work suggests that pebbles, if they lead to the kind of core formation I think they do, you're going to end up with very stratified cores. And then Mars gets slammed with the Borealis Basin impact, or it just gets hit by this little impactor that makes the Borealis Basin, it makes little tiny moons, but Mercury gets slammed with something really big. And that strips mantle and potentially mixes the whole core. But this is just a hypothesis. This isn't. Yeah, but I do think when you have this shell, when you have this onion-like thing, you can have convection at first. Because if you do have a super adiabatic thermal gradient, at first you'll have to, that'll move through the core and as it relaxes to an adiabat. And that'll drive some convective motion and some geodynamo. A corollary of this is that potentially these onion-like dynamos are really weird, and that's why the recorded magnetic field on places like the moon and Mars are really weird, is because they recorded not a single cell dynamo, but some like multi-cell dynamo, and so you see all these higher order terms. Yeah. So that's right. So that's actually my work is well, it's really the work of my student Jeremy Brooks, but our work builds off of work done by Kaveh Pahlavan, who was in Nice with me. And what Kaveh did was Kaveh worked on the Earth problem. So he suggested that if you started with the moon forming from a disk that was in the equator of the planet, which is where you'd expect it to be, the 0.5% of highly siderophile that the highly siderophile elements suggest that the Earth accreted post moon forming impact, that can be translated into a certain amount of material that flew by the Earth. You can calibrate how much material is left in the disk, and from that figure out what the violence of the flybys were. And what he showed is that it actually does a great job inclining the moon to about the right level that it's inclined today. So for the Earth, it just like pushes the moon around in space. Whereas with Venus, which is much earlier, which the hypothesis is that it would have been much earlier, you could lose the moon completely. Yeah. The accreting by Pebble accretion means that it doesn't mean that your mantle is always cold. Let's put it that way. You're still releasing a lot of gravitational potential energy. You're just doing it in a different way than through planetesimal or embryo bombardment. And so you could still create a mantle magma ocean. I think it likely would be shallower mantle magma ocean, and you'd be the That's kind of my point. Yeah. Mars, for example, if you have a shallow magma ocean. Right. It takes 40 or 50. Right. Yeah. So the idea effectively is you're adding sulfur, and the amount you're adding is it's varying a small amount as you accrete the planet as the core grows. But because the core forming liquids are effectively dripping to the top of the core as opposed to coming in large quantities, you're building this very smooth but very stable stratification. That's a hypothesis. I mean, that's it's not in the talk for a reason, but that's the idea.
Thanks again.